This is a laser. Simple, reliable, and incredibly fast. But this tiny component can detect it instantly. Using just this principle, I built a laser-based security system which can detect intruders the moment they cross this beam. But how does a beam of light turn into an electrical signal? So in this series, I'll show you exactly how the system works and how you can build one yourself using very simple components. By the end, you won't just understand it, you will be able to design your own. And it all starts here. But before we begin, let's understand how the system works. Here on my terrace, I've installed these laser modules, each one precisely aimed at the photodiode on the opposite side. As long as this beam remains uninterrupted, the system knows that everything is secure. But the moment someone walks through this area and blocks the beam, the output of the photodiode changes instantly. This change is detected by the Arduino immediately, which triggers the alarm. At the same time, this ESP sends the user a notification through Telegram, ensuring real-time intrusion detection. But that's just the basic functionality, because a real security system must also handle tampering, because an intruder might try to disable the system by just cutting the wires. So to address this, the system continuously monitors the integrity of the wiring itself. To test the tamper protection, I am going to cut the sensor wire using these pliers. This creates a short circuit between the power lines. Normally, this should crash the system, but instead our system detects it and immediately raises an alarm. So now that we know how this system works, we need several critical components to bring this system to life. Let's go through them one by one. So the raw mains power is first converted into DC using this power adapter, which is then precisely stepped down using this MP1584 DC to DC buck converter, which gives us precisely the voltage we need. This ESP8266 acts as a master controller for our system. It handles Wi-Fi, manages time-based arming, and notifies user as soon as intrusion is detected via Telegram. This Arduino acts as a real-time response unit. It continuously monitors for the intrusion signals, and the moment it detects one, it turns the siren on through the relay. These 650 nanometer laser modules act as the system's tripwire. These photodiodes act as the electrical eye for the system. These continuously monitors the beam produced by the laser modules and convert that optical signal into an electrical signal. These NPN transistors act as the low-speed switching devices, which allows the Arduino to safely control the relay. These relay act as an electronic switch and allows the Arduino to control the siren. And for the overall protection of the system, we will use a glass fuse. But arriving at this final design was not straightforward. So I first tried using an ultrasonic sensor, but it wasn't reliable enough for this application. Then I tested a PIR sensor, but it also didn't provide the consistent detection that I needed. After all the testing and failed attempts, I finally arrived at the design that was precise, reliable, and efficient. Now it was time to bring the system to life. The power adapter required a female connector, which I didn't have, so I improvised and used a screw terminal to create a solid and secure connection. At first, I relied on LM2596 buck converters to step down to 12V supply, but during testing, the microcontroller began behaving unpredictably. It was clear the issue wasn't the code, it was the power. So I switched to MP1584s and added filter capacitors to get a clean and stable voltage. With the power supply stable, everything now depended on one component, the photodiode. If it failed, the entire system would fail. At its core, a photodiode is basically a specialized PN junction diode with P-type semiconductor on one side and N-type semiconductor on the other, forming a depletion region between them, with holes on the P side and electrons on the N side acting as charge carriers. At the junction, these charges recombine and create an internal electric field, which when operated in reverse bias condition becomes even more stronger. When photons in the light hit this depletion region, it excites electron to the conduction band, generating an electron-hole pair. The electric field separates these charges, producing a small photocurrent. But that was just the theory. To verify it, I connected a multimeter and exposed the photodiode to the laser, and sure enough, it generated a current of around 5 microamps. With everything ready, it was time to introduce the brain of the system, the ESP. But to integrate it reliably, it needed a proper breakout board, and since none was available, I designed one myself. With the ESP properly connected to the breakout board, it was time to write the code. But to keep this video focused, I'll cover the complete wiring and code in a separate detailed video. With everything tested and verified, I began assembling the system. To temporarily mount the components, I used double-sided tape. With the components in place, it was time to organize the wiring. To properly connect the external components, I used the screw terminals. And now, for the eyes of the system, the laser modules and the photodiodes, I used PVC pipes as protective casings and sealed them with plexiglass to make them water resistant. At this point, I want to emphasize the importance of safety. Whenever you are using any power tool, always wear proper protective gears. Once the waterproof casing was ready, I soldered the photodiodes onto a perf board and secured it inside with hot glue. With the internals complete, here's how the module looks. With the module ready, it was time to take it outdoors. To mount the photodiodes and the lasers, I used wall plugs and secured them firmly using screws. But during alignment, I ran into a big issue. The alignment process was unforgiving, so I went back, redesigned the sensor stage and used 2 photodiodes in parallel to increase the sensing area. With everything in place, it was time for real world testing. So the system works and Julie approves. As you can see, the system is working reliably and exactly as intended. However, there is still a few improvements to be made, like making the alignment process a bit more forgiving. But this is just a prototype. In the next video, we'll be taking this a step further by refining the design, adding a custom PCB and a professional grade enclosure, making this a truly commercial grade system. Until then, keep building and I'll see you in the next one.